Tonight, we're going to point the most powerful telescope ever built at a dot of light so far from Earth that sunlight takes more than 5 hours to reach it. Tonight, we're going to measure the heat coming off that dot. And tonight, we're going to find out that the dot, the one we stopped calling a planet 20 years ago, the one we filed away under too small, too cold, too distant to matter, is doing something that no other world in this entire solar system does. Not one. Not a few. Not a handful we haven't examined carefully. Not one. The telescope is the James Webb Space Telescope. The dot is Pluto. And what it found when it looked, really looked, in wavelengths no instrument had ever used on Pluto before, is the reason you are watching this. If you have been here before, welcome back. If this is your first time, settle in. This is going to take a while. Not because the topic is slow, but because the topic is deep, and deep things deserve the time they need. Before we go any further, if you find yourself staying, if this is the kind of content you come back to, subscribe. It helps more than you might think. Now let's begin. There is a specific kind of forgetting that happens in science. It is not the forgetting of ignorance, the kind where you simply don't know a thing exists. It is a different kind. The kind where you know a thing exists, you give it a name, you study it briefly, you put it in a category, and then you move on. The category does the work that attention used to do. The label becomes a substitute for curiosity. And the world inside the label, the actual physical place, keeps doing what it was always doing, completely indifferent to the fact that you have moved on. That is what happened with Pluto. Pluto was discovered in 1930 by a young astronomer named Clyde Tombaugh, working at the Lowell Observatory in Arizona. For 76 years it was the 9th planet in the solar system. It had that status not because anyone had studied it in detail, but because the category felt correct. It was out there, orbiting the Sun, roughly round, and we didn't have any better ideas about what to do with it. For most of those 76 years, Pluto was a faint smudge in even the best telescopes. We couldn't resolve its surface. We couldn't measure its atmosphere properly. We knew it was cold. We knew it was small. And we knew it was very far away. Those 3 things were enough to make it feel understood. Then, in 2006, the International Astronomical Union voted. They decided that a planet must, among other things, gravitationally dominate the region of space around its orbit. Pluto, sharing the outer solar system with a large population of similar icy objects in the region we now call the Kuiper Belt, did not qualify. It became a dwarf planet. The textbooks were rewritten. School children wrote letters. Astronomers received angry emails. And then, relatively quickly, the world moved on. The cultural message of the demotion was not just that Pluto was reclassified. The message was, Pluto is not special. It is one of many. It is a leftover piece of the outer solar system, a chunk of ice and rock that never grew large enough to clear its neighbourhood. It belongs to a category of things we can note and file, rather than a category of things we must urgently understand. And then, 9 years later, on July 14, 2015, NASA's New Horizons spacecraft flew past Pluto, and the filing system broke. What New Horizons revealed was not what anyone had expected. In the hours of useful close-up data it returned before disappearing deeper into the outer solar system, the spacecraft showed a world of striking geological complexity. There were mountains made of water ice rising more than 3,000 meters above the plains, comparable in height to the Appalachian Mountains, and at temperatures where water ice is not soft and yielding, but rigid as granite. There were smooth, crater-free plains of nitrogen ice that glowed pale and luminous against the darker surrounding terrain. There was a heart-shaped feature, enormous and bright, covering a region roughly as wide as Texas and Oklahoma combined, a glacier of nitrogen, methane, and carbon monoxide that had been sitting there, gradually renewing itself, for an unknown but geologically brief span of time. There were no craters in the brightest parts of that heart. No craters. On a world 4.6 billion years old, the absence of craters on a surface is one of the loudest things a planetary scientist can hear. Craters accumulate over time. They are the record of impacts, the geological clock of a surface's age. Their absence means one thing. Something erased them. Something renewed the surface. Something is still happening here. There was a haze in the atmosphere, blue layers of it, rising hundreds of kilometers above the surface, visible in the backlit images New Horizons sent back as it passed through Pluto's shadow. The haze was not expected to be so thick, so layered, so blue. New Horizons gave us all of this in 9 days of useful data from a spacecraft travelling at roughly 0 kilometers per hour that never slowed down and never looked back. It was a single pass, a single snapshot, a photograph taken from a moving vehicle. It told us that Pluto was strange. It did not have the time to tell us why. That is what the James Webb Space Telescope came back for. But to understand what JEST found when it looked, you first need to understand what JWEST actually is, and why it sees Pluto in a way nothing that came before it ever could. Most of us think of telescopes as very powerful cameras. That intuition is not entirely wrong. Telescopes do collect light and form images. Hubble, the telescope that gave us a generation of spectacular visible light photographs of galaxies and nebulae and star clusters, is in effect a very large camera in space, pointed away from the Sun and Earth to give it the darkest possible sky. When people think of space telescopes, they think of images, the pillars of creation, the deep field, the face on spiral galaxies with their arms of blue and gold. James Webb is different. Not entirely, it can produce images too, and some of its early photographs were striking. But the instrument at the centre of what JWST did with Pluto is not a camera in any normal sense. It is something called a spectrometer, and specifically an instrument called MIRI, the mid-infrared instrument. And MIRI does not take photographs. It reads heat. Let's slow down and make sure this is clear, because it matters for everything that comes after. Every object in the universe that has a temperature above absolute zero, the theoretical minimum temperature where all thermal motion stops, emits radiation. Not just light that we can see, radiation across the entire electromagnetic spectrum. A human body standing in a dark room is invisible to an ordinary camera. But to a camera sensitive to infrared radiation, the kind of radiation produced by objects at human body temperature, that person glows like a lantern. Infrared cameras are used in night vision equipment, in search and rescue operations, in the thermal imaging systems that let firefighters see through smoke. They don't see reflected light, they see emitted heat. The Sun's surface is at roughly 5,500 degrees Celsius. Objects that hot emit most of their energy as visible light, the wavelengths our eyes evolved to detect. But cooler objects emit their energy at longer, lower energy wavelengths. The planet's surface at temperatures of tens or hundreds of degrees emits mostly in the infrared. At Pluto's surface temperature, around minus 229 degrees Celsius, or roughly 44 Kelvin, an object emits radiation primarily in the mid-infrared range, at wavelengths measured in micrometers far beyond what any ordinary camera can detect. MIRI was built to operate in exactly this range. It can detect infrared light at wavelengths between roughly 5 and 28 micrometers. This is significant for Pluto in two specific ways. First, it means MIRI can directly measure the thermal emission from Pluto's surface, not sunlight reflected off the surface, but the heat that Pluto itself is producing and radiating. Second, it means MIRI can detect the chemical signatures of specific compounds in Pluto's atmosphere, because different molecules absorb and emit infrared radiation at specific characteristic wavelengths. Reading those wavelengths is like reading a barcode. Each chemical leaves its own mark in the spectrum. Before JWS, every telescope that tried to study Pluto in the infrared lacked the sensitivity to do this cleanly. There was a particularly frustrating problem. Pluto and its largest moon, Charon, orbit each other at a relatively close distance, only about 19,500 kilometers apart, and from Earth, even from orbit, the two worlds appear so close together that most instruments blurred their signals together. Scientists studying Pluto's thermal emission were actually studying a combined Pluto plus Charon signal, with no way to separate which heat was coming from which world. Every thermal model of Pluto was built on data that was, at least partially, wrong, because it included Charon's contribution without being able to subtract it. JWST's MIRI changed this. In October of 2022, JWST visited Pluto 6 times over the course of a few days, 6 separate observations, spaced to capture different faces of Pluto as it rotated, covering the full range of longitudes. At the wavelengths MIRI operates in, and at JWST's sensitivity, the telescope was able to separate Pluto's thermal signal from Charon's for the first time in history. Not approximately. Clearly, definitively, what it measured as Pluto rotated and different terrains came into view was a light curve, a record of how Pluto's infrared brightness changed over time. Different parts of the surface emit different amounts of heat, depending on what they're made of, how reflective they are, and how efficiently they absorb and release energy. The light curve encodes all of this. A skilled planetary scientist looking at a thermal light curve can extract the surface properties, the composition of different terrain types, and, this is the crucial part, whether the atmosphere is contributing to the thermal signal in a way the models didn't predict. There is something worth pausing on here, because it captures a particular kind of scientific strangeness that doesn't get enough attention. JWST cannot resolve Pluto as a disk. At 5.5 billion kilometers, even JWST's enormous 6.5 meter primary mirror, the largest ever sent to space, cannot produce an image of Pluto that shows individual surface features. Pluto, in JWST's field of view, is still in effect a point of light. What MIRI measures is the total infrared emission from that point, integrated across the entire visible hemisphere of the planet. And yet, from that single point of light changing over time, a trained planetary scientist can read the planet's surface. Not in the way a photograph reads it, not with geography and coastlines and mountain ranges, but in a different way. A thermal way. The brightness rises as the glacier rotates into view. It falls when the darker, less thermally active terrain faces the telescope. Different wavelengths respond differently because different surface compositions have different emissivity profiles. By watching the point of light breathe and shift across 6 visits spaced over Pluto's rotation, the team built a thermal portrait of a world they could not see. This is not a novel technique in planetary science. Thermal light curves have been used to study distant bodies for decades, but JWST's sensitivity and the specific wavelength range of MIRI brought a new level of precision, enough to cleanly separate Pluto from Charon, enough to detect the haze contribution, enough to distinguish methane ice terrain from nitrogen ice terrain from dark organic terrain. A technique that had been applied with limited success to this system for years suddenly worked the way it was always supposed to. When the team compared Drest's measurements to their best models of what Pluto should look like, one thing stood out immediately. The haze was glowing. Not the surface. Not the gas. The haze, that layer of organic particles suspended in Pluto's upper atmosphere, the same layer that had appeared blue and mysterious in New Horizons' backlit images 7 years earlier, was emitting measurable mid-infrared radiation. The heat signal from Pluto didn't match the surface-only models. There was an extra contribution. It was coming from the atmosphere, from high above the surface, from the haze. That signal had been predicted 8 years earlier, by a researcher who at the time was told his idea was crazy. But before we get to that story, it helps to know what scientists thought they already understood about Pluto's atmosphere, and exactly where and why they disagreed. Pluto has an atmosphere. This surprises many people when they first hear it. The idea of an atmosphere on a world this small, roughly 2/3 the diameter of Earth's moon, in a place this cold, this far from the sun, feels counterintuitive. Atmospheres belong on bigger worlds, warmer worlds with enough gravity to hold their gases down. But Pluto does have an atmosphere, thin as it is, and that atmosphere is in some ways one of the strangest in the solar system. The main ingredient is nitrogen, the same element that makes up roughly 78% of Earth's air. Beneath the nitrogen, in smaller but significant quantities, are methane and carbon monoxide. These are volatile compounds, substances that shift between solid ice and vapour depending on temperature. And Pluto's surface is cold enough that most of them freeze out onto the surface most of the time. The atmosphere exists because small amounts of these ices are always sublimating, converting directly from solid to gas, driven by the faint but real energy of the distant sun. The atmospheric pressure at Pluto's surface is extraordinarily low. It is roughly 10 to 100 times lower than the atmospheric pressure on Mars, which is itself about 150 times lower than Earth's. It is, by any intuitive standard, barely an atmosphere at all. And yet, it is complex. It is layered. It behaves in ways that still, as of a few years ago, scientists actively disagreed about. The central disagreement was about temperature. Specifically, what controls the temperature of Pluto's upper atmosphere? On Earth, the answer to that question involves several players: sunlight absorbed by gases, greenhouse effects from carbon dioxide and water vapour, circulation patterns, the behaviour of the lower atmosphere interacting with the upper atmosphere. On Mars, the answer is somewhat simpler: a thin carbon dioxide atmosphere absorbing and radiating heat in a relatively direct way. On Titan, Saturn's largest moon, the answer involves a thick nitrogen atmosphere with complex photochemical haze, and the temperature structure is well studied. On Pluto, scientists knew the atmosphere was colder than their models predicted. Instruments on New Horizons measured the temperature of Pluto's upper atmosphere and found it was significantly colder than the models based on gas behaviour alone would suggest. Something was cooling it more efficiently than expected. The question was what? One camp argued that carbon monoxide gas, in small quantities, was doing the cooling, absorbing heat and radiating it away efficiently enough to explain the measured temperatures. This was the more conservative hypothesis. It fit reasonably well within existing frameworks for thin planetary atmospheres. A second camp had a more radical proposal. In 2017, a researcher at the University of California, Santa Cruz, named Shi Zhang, published a paper arguing that the haze particles, those blue, complex organic particles suspended in Pluto's upper atmosphere, were the dominant cooling agent. The haze in his model absorbed sunlight during the day, heated up, and then radiated that heat back into space as infrared radiation. Not gas molecules doing the work. Particles, a planetary thermostat made of organic material floating in the cold air above a frozen world. This was, as Zhang himself later recalled, described by some colleagues as a crazy idea. It was an unconventional hypothesis for a specific reason. No other atmosphere in the solar system was known to be primarily cooled by particle haze. Gas molecules cool atmospheres. That is the established model. The idea that tiny suspended particles could dominate the entire energy budget of a planetary atmosphere, could be the main mechanism by which that atmosphere loses heat, was truly unusual. It required either that Pluto was uniquely strange in this way, or that we had been wrong about some fundamental aspect of how haze behaves in cold, thin atmospheres. But the hypothesis had one saving quality that separated it from mere speculation. It made a testable, precise, falsifiable prediction. If the haze particles are cooling Pluto's atmosphere by radiating heat into space as infrared emission, then the haze layer should be detectably bright in mid-infrared wavelengths. The haze itself should glow, not just the surface, not just the gas. The haze up in the atmosphere should emit a distinct thermal signature measurable with the right instrument. The problem was that no instrument sensitive enough to test this prediction existed in 2017. The sensitivity required was beyond what any operating telescope could achieve for an object at Pluto's distance. Zhang and his collaborators published the prediction and noted, in the paper, that it would require future instruments, specifically instruments of the kind that would eventually fly on the James Webb Space Telescope. Just launched on Christmas Day 2021, it arrived at its final orbital position around the Sun in early 2022. It began science operations that summer. And in October of 2022, it pointed Miri at Pluto for the first time. The prediction had been waiting 8 years for this moment. In October of 2022, 6 observations, 6 visits to a single point in the sky, 5.5 billion kilometers from Earth. The science team organized the observations carefully. They needed to catch Pluto at different rotational positions, different faces of the planet as it turned, so that the light curve they measured would cover the full range of terrains on the surface. This was necessary because different regions of Pluto have different thermal properties. The nitrogen glacier of Sputnik Planitia is bright and reflective, and it behaves differently from the dark, cratered highlands or the methane ice-capped mountains at higher latitudes. To understand the full thermal picture, you need to watch the entire planet rotate. Over those 6 visits, Mary measured Pluto's brightness at wavelengths of 15, 18, 21, and 25 micrometers, well into the mid-infrared range that had never been cleanly observed for Pluto before. The measurements were precise enough to separate Pluto's emission from Charon's for the first time. They were precise enough to see Pluto's brightness changing as it rotated, different terrains passing in and out of view, each one contributing its own thermal signature to the total signal. And when the team modelled what they expected to see, built thermal models using everything they knew about Pluto's surface composition, reflectivity, temperature, and atmospheric structure, they found that the surface alone could not explain the data. There was too much infrared emission at the measured wavelengths. The models that included only surface thermal radiation fell short. To match the observations, you needed an additional source of emission. You needed the haze. When they added the haze layer, the organic particle cloud hanging in Pluto's upper atmosphere, to their thermal models, the fit improved dramatically. The observations matched. The prediction made 8 years earlier, which colleagues had called a crazy idea, was confirmed. Pluto's atmospheric haze controls the temperature balance of its atmosphere. The particles absorb solar energy during the day, heat up, and radiate that heat into space as mid-infrared emission. This keeps the upper atmosphere colder than it would otherwise be. It is, in the most technical language, a radiatively active haze dominating the atmospheric thermal balance. In less technical language, Pluto has a planetary thermostat. It is made of organic particles. And it works unlike any other thermostat in the solar system. This finding was published in June of 2025 in the journal Nature Astronomy, in a paper led by Tanguy Bertrand and co-authored by Shisang, among others. A second paper, published in April of 2025 in Astronomy and Astrophysics, covered additional details of the spectroscopic observations. These were the first papers from J. West's observations of Pluto, and they changed what we knew about this world. But to understand why this matters, why a haze thermostat is truly strange and not just an interesting technical footnote, it helps to think about atmospheres in general and what role energy balance plays in making a world livable or unlivable, active or static. An atmosphere's temperature is controlled by a balance between energy coming in and energy going out. Energy comes in primarily as sunlight, photons from the sun absorbed by the atmosphere and the surface. Energy goes out as radiation emitted back into space. The temperature settles at whatever value makes these two flows equal. On Earth, that balance is managed mainly by greenhouse gases, water vapor, carbon dioxide, methane, that trap outgoing radiation and warm the lower atmosphere, while other processes cool the upper atmosphere. The temperature profile of Earth's atmosphere is a record of all these processes operating together. On Pluto, the balance works differently. The sunlight arriving at Pluto is about 1/100 times weaker than what reaches Earth, the inverse square law applied across 5.5 billion kilometers. With that little energy input, you might expect Pluto's atmosphere to be simple, a thin layer of gas, barely absorbing anything, barely doing anything, in effect static. The fact that instead it contains a dynamically active haze layer that dominates the entire energy budget is significant. It means that even at these extreme distances, even with these faint inputs of solar energy, something complex is happening. It also means that Pluto's atmosphere is unlike every other atmosphere we have studied in detail in the solar system, in the specific sense that no other atmosphere is known to be primarily controlled by particle haze. Gas molecules do this work everywhere else. On Pluto, particles do it. Whether this is because Pluto is uniquely strange, or because we simply haven't looked carefully enough at other haze-bearing worlds, is now an open question. The May 2023 follow-up observation added more. In that session, MIRI spectrometer captured a high-quality mid-infrared spectrum of Pluto and its atmosphere, covering wavelengths from 4.9 to 27 micrometers, a range that had never been measured for Pluto before, because no instrument before JUST had the sensitivity to do it cleanly at this distance. The spectrum revealed chemical signatures of methane ice, deuterated methane, ethylene ice, and the haze particles themselves, a chemically richer picture of Pluto's surface and atmospheric chemistry than had ever been available. This was the full confirmation. The haze is there, it is composed of complex organic particles, similar in some ways to those found in Titan's atmosphere, and it is doing exactly what Zhang predicted in 2017. The crazy idea turned out to be right. But underneath that haze, the surface is doing something that is equally significant and, in its own quiet way, equally strange. Because Pluto's surface should be frozen solid, it should be static, it should be piled with craters accumulated over billions of years of bombardment. And it is none of those things. Let's establish the expectation first. because the surprise only lands if you know what the expectation was. Pluto is roughly 4.6 billion years old. The solar system formed 4.6 billion years ago, and Pluto was part of that formation, a planetesimal in the outer disk, accreting mass during the early chaotic period when the planets were still gathering material. By the time the solar system settled down and the heavy bombardment period ended, Pluto was a small, cold world in the outer solar system, receiving only a tiny fraction of the sun's warmth. At those temperatures, around -229 degrees Celsius, most chemical processes slow to near nothing. Ice does not flow. Rock does not erode. The world, you would reasonably assume, simply sits. Over 4.6 billion years, such a world should accumulate craters. Lots of craters. The outer solar system is not empty space. It contains billions of small bodies, ranging from dust to asteroid-sized chunks, and over geological time, even a slow rate of impacts adds up. Old surfaces in the solar system are heavily cratered. The Moon's highlands, among the oldest terrain in our planetary neighbourhood, are saturated, so many craters that new impacts simply overwrite old ones. Mars has ancient cratered plains. Mercury is covered in them. The expectation for Pluto, old, cold, distant, geologically quiet, was the same. New Horizons arrived and found something else entirely. The heart of Pluto, Tombor Regio, the bright heart-shaped feature that became the defining image of the flyby, is dominated by a region called Sputnik Planitia. The western lobe of the heart, a vast nitrogen glacier roughly 1,000 kilometers across. And Sputnik Planitia has almost no craters. The surface is smooth and pale and divided into irregular polygonal cells, each one ranging from roughly 20 to 40 kilometers across, ringed by shallow troughs. There are no large impact scars. The terrain is geologically young. Estimates from the New Horizons team suggested that some regions of Sputnik Planitia may be less than 10 million years old. 10 million years. For context, the solar system is 4.6 billion years old. Dinosaurs went extinct 66 million years ago. Some parts of Pluto's surface are younger in geological terms than the mass extinction that ended the age of dinosaurs. On a world we thought was frozen in time 4 billion years ago. What is erasing the craters? The answer lies in the nature of nitrogen ice under conditions of very slight heat. Pluto's interior, despite being cold by human standards, still contains heat from the decay of radioactive elements, the same heat source that keeps the Earth's interior warm and geologically active, scaled down dramatically for Pluto's smaller size. That gentle warmth is enough to drive convection in the nitrogen ice of Sputnik Planitia. Convection in ice works like convection in any viscous fluid. Warmer material near the base of the ice layer becomes slightly less dense, rises, spreads across the surface, cools, and sinks back down. The cells you see on Sputnik Planitia's surface, those polygon patterns, are the surface expression of this convective motion. They are the imprint of a slow churning that has been happening for geological time, gradually refreshing the surface, filling in any crater that forms before it has time to become permanent. The mountains at the edges of Sputnik Planitia are made of water ice. At -229 degrees Celsius, water ice does not flow or deform, it behaves like rock. These mountains, some of them rising 3,000 meters above the plains, are solid and stable. They are the ancient terrain, the older highlands. The nitrogen glacier inside its borders is relatively young. Dwest's thermal observations added a layer to this picture. The light curves measured in 2022 showed clear differences in thermal properties across different terrains. The nitrogen-rich regions of Sputnik Planitia have distinctive infrared signatures, bright, reflective in some wavelengths, thermally unique in others. The methane ice-capped mountainous regions show different properties. The dark, cratered highlands read differently again. The thermal map that Dwest produced, even without the resolution to see individual features, revealed the compositional diversity of Pluto's surface in a way that ground-based observations never could. There is a particular strangeness in what the convection cells imply about time. On Earth, when we talk about something being geologically young, we usually mean tens of millions of years. A blink of geological time, but still vast by any human measure. The dinosaurs are young in geological terms. The Atlantic Ocean, which began opening roughly 180 million years ago, is young. The youngest large geological feature on Earth's surface is probably something that formed in the last few million years, a volcanic island, a recent rift valley. The youngest parts of Sputnik Planitia are estimated to be, as mentioned, less than 10 million years old in some regions. But what is startling is not just the age. It is what that youth requires. For a surface to remain this crater-free, it is not enough for new ice to be deposited from above. The material below must be actively moving. The convection cells are not a theoretical implication drawn from the surface's appearance. They are a physical necessity. The surface is crater-free because the ice beneath it is circulating, slowly, patiently, inevitably, turning over at a rate that erases impact craters before they can accumulate. That circulation requires heat from below. Not much heat, a tiny fraction of what drives Earth's plate tectonics. But some heat. Consistent heat. The radioactive elements decaying inside Pluto's rocky core, uranium, thorium, potassium, release energy as they decay, and that energy diffuses outward through the ice mantle. At the base of the nitrogen glacier, it provides just enough warmth to keep the ice slightly warmer than the cold above, creating the density difference that drives the convective flow. A geological engine running on radioactive decay in the cold of the outer solar system, keeping a glacier alive for billions of years. What this all means is simple to state and strange to sit with. The youngest surface in the solar system per unit of geological time may be on one of its oldest, smallest, most distant worlds. The geological activity on Pluto is not explosive or dramatic the way Earth's plate tectonics or Mars's ancient volcanic activity was. It is slow, patient, steady, but it is real, and it is connected to everything else that makes Pluto strange. Because the glacier that keeps renewing the surface is also the engine that drives the atmosphere above it. Think of Pluto's heart not as an image, not as the bright feature in a flyby photograph, but as a machine. It is a machine that has been running for a very long time. It runs on the slight difference between day and night temperature, on the faint sunlight of the outer solar system, on the properties of nitrogen at temperatures near absolute zero. It is not fast, it is not dramatic, but it is continuous, and it drives almost everything that happens on Pluto's surface and in Pluto's atmosphere. Here is how it works. Sputnik Planitia, the nitrogen glacier, sits in a basin that is roughly 2.5 kilometers lower than the surrounding terrain. It is wide, flat, and made of material that sublimates readily, that is. It converts from solid ice directly to vapor when it absorbs even a small amount of energy. The sunlit portions of the glacier, even receiving only 1/1600th the sunlight that Earth does, absorb enough energy during Pluto's long day. Pluto's day is about 6.4 Earth days, to drive sublimation at a measurable rate. Nitrogen vapor rises from the surface of the glacier and enters the atmosphere. This process creates a local atmospheric pressure gradient. The sublimating nitrogen raises the pressure slightly over the sunlit portions of the glacier. Higher pressure at one location drives airflow toward lower pressure regions. On Pluto, this means nitrogen-laden air flows outward from the glacier, moves across the surface, encounters the colder, shadowed portions of the planet, and condenses back down, nitrogen vapor freezing out onto the surface as fresh ice, in the colder highlands and in the darker regions away from the main glacier. This cycle repeats every Pluto day: sublimation during the sunlit hours, condensation during the dark hours, and a continuous flow of nitrogen gas and then nitrogen ice connecting the two processes. The glacier is, in this way, acting as a global air conditioner, absorbing solar energy in one place and releasing it as condensed ice in another. The winds this system drives are not strong by Earth standards. Models built from New Horizons data suggest the winds near the surface reach roughly 20 to 30 kilometers per hour in the most active regions, a stiff breeze by human experience, but relatively modest for a planetary atmosphere. What is significant is the direction. The winds circulate westward around Pluto, curiously opposite to the direction of Pluto's own rotation. This counter-rotational wind pattern is a direct consequence of the Coriolis effect on a slowly rotating world, combined with the specific geography of the sublimation source. The winds are not just a curiosity of fluid dynamics. They do real work on the surface. They carry nitrogen frost to new locations. They sculpt patterns in the volatile ice, creating streaks and dunes in regions where wind-blown material accumulates. Some of the dark streaks visible on Sputnik Planitia in New Horizons imagery are thought to result from wind-driven deposition of dark material from the glacier's edges. West's thermal observations added evidence consistent with this picture. The light curves showed different thermal responses at different longitudes: warmer where sublimation is most active, cooler where condensation dominates. The thermal properties of the nitrogen-rich terrain differ markedly from the surrounding highlands, and those differences are consistent with a surface that is being actively refreshed by the sublimation-condensation cycle rather than sitting static. The glacier, the winds, the haze, the thermal cycle, they are all part of the same system. The heart drives the atmosphere. The atmosphere feeds the haze. The haze controls the temperature. The temperature governs how fast the glacier sublimates. The system is self-regulating, self-sustaining, and has apparently been running in some form for a very long time. But there is a point at which the system leaks. Not dramatically, not catastrophically, but nitrogen molecules rising from the surface, carried upward by atmospheric circulation, eventually reach the top of the atmosphere, the exosphere, the region where Pluto's gravity becomes too weak to hold them securely. And some of them escape. When gas escapes a planetary atmosphere, most of it goes nowhere. It disperses into space, joins the solar wind, drifts outward. But Pluto is not alone. It is in a binary system with a moon that is, for a moon, extraordinarily large relative to its planet. Charon is more than half the size of Pluto. And Charon is close. Close enough that some of what Pluto loses does not escape the system. It just goes next door. Everything that holds an atmosphere also, eventually, loses it. This is not a Pluto-specific problem. It is a universal one. Atmospheres persist because planetary gravity is strong enough to hold gas molecules against the thermal energy trying to push them outward. But thermal energy does not distribute evenly among gas molecules. At any given temperature, some molecules are moving faster than average, some slower. At any given moment in the upper atmosphere, some molecules have enough thermal velocity to reach escape velocity, the speed needed to leave the planet's gravitational influence entirely. On Earth, this process, called atmospheric escape, or Jeans escape, after the astrophysicist who first described it mathematically, operates extremely slowly. Earth's gravity is strong. The molecules most vulnerable to escape are the lightest ones, hydrogen and helium, and Earth loses them over geological time, not over human timescales. Heavier molecules like nitrogen and oxygen have in effect zero probability of escaping, and Earth's atmosphere is stable over millions of years. On Pluto, the situation is different. Pluto's gravity is about 1/15 of Earth's. Its escape velocity, the speed needed to leave its gravitational pull entirely, is roughly 1.2 kilometers per second, compared to 11.2 kilometers per second for Earth. For a molecule at the temperature of Pluto's upper atmosphere, this threshold is reachable. Not by most molecules, and not quickly, but by enough molecules, and consistently enough over time, that the escape rate is real and measurable. New Horizons detected Pluto's atmosphere extending as far as 1,100 kilometers above the surface, much higher than expected for a world of this size. This extended atmosphere is the outer edge of the escape region, where the most energetic molecules are crossing the line between Pluto's control and freedom. The rate of escape is relatively modest. Estimates suggest Pluto is losing a small fraction of its atmospheric nitrogen over geological time, not dramatic quantities on any human timescale. But the escape is real. The molecules most easily lost are also the lightest. Methane, one of Pluto's atmospheric minor components, is lighter than nitrogen. In the upper atmosphere, methane molecules are more likely to reach escape velocity than nitrogen molecules. They escape preferentially. And because they escape preferentially, they are the molecules most likely to drift away from Pluto and into the space around it. Most of what escapes truly escapes, disperses into the solar wind, becomes part of the interplanetary medium, is lost permanently. But a fraction of the escaping methane does something unexpected. It finds a surface nearby. Here is where the geometry of the Pluto-Charon system matters in a way that doesn't get enough attention. Pluto and Charon are not simply a planet with an orbiting moon. They are technically a binary system. Both bodies orbit their common centre of mass, which happens to lie between them outside Pluto's surface in open space. Charon is so massive relative to Pluto that the centre of gravity does not lie inside Pluto itself. This is unusual in the solar system. Most planet-moon systems have their centre of mass well inside the planet. Only the Pluto-Charon system, among known bodies orbiting the Sun, has its centre of mass outside the primary world. The consequence of this geometry is that the two worlds are gravitationally bound to each other in a way that shapes what happens to escaping gas. A methane molecule that reaches escape velocity from Pluto and begins moving outward is not immediately lost to interplanetary space. It is still within the combined gravitational sphere of influence of the Pluto-Charon system. Molecules moving in the direction of Charon, or those with trajectories that intersect Charon's orbital path, have a real probability of being captured by Charon's gravity rather than lost to space entirely. It is not a high probability for any individual molecule, but summed across billions of years and across the continuous flow of escaping methane, it adds up to something physically significant. Charon is 19,500 kilometers from Pluto. In astronomical terms, this is nothing, roughly the distance you could drive a car in 2 weeks at highway speed. For a molecule that has achieved escape velocity from Pluto's surface, the distance to Charon is trivial. the molecule crosses it in under an hour, and when it arrives at Charon, it finds a world with no atmosphere of its own, no significant sublimation cycle, and, at its poles, some of the coldest, darkest surfaces in the outer solar system. Those poles are cold traps. A cold trap in planetary science is a region so cold that even highly volatile substances freeze and stay frozen, with in effect no sublimation. The poles of Charon in deep shadow during the long Plutonian winter are cold enough to trap methane permanently. Methane molecules arriving from Pluto do not drift on, they settle. And then something happens to them. Charon's poles are not white or grey, the way you might expect a water ice world to look. They are dark reddish brown. That colour is not Charon's native rock or ice, it is chemistry. The chemistry of Pluto carried across empty space, frozen onto a neighbouring moon, and transformed by ultraviolet radiation into something more complex and more permanent. Webb confirmed this process was real, and revealed it in more detail than ever before. But to understand what it confirmed, we need to understand what it found when it finally looked at both worlds separately, something no telescope had ever cleanly achieved before. This is the finding that sits most quietly and most persistently at the back of the mind after you've understood it. Not the haze thermostat, as striking as that is, not the geological youth of the surface, as unexpected as that was, not even the temperature readings. This one. The finding that Pluto is slowly, continuously, over billions of years, giving its own atmosphere to its moon. Let's make it concrete. Charon has no atmosphere. It is a world of water ice and rock, roughly 1,200 kilometers across. Smaller than Pluto, but still a substantial object by the standards of the outer solar system. Its surface, as photographed by New Horizons, is mostly grey-white, water ice mixed with some rock, with a network of fractures and canyons suggesting a complex geological history of its own. The equatorial belt of fractures tells a story of an ancient interior that was once liquid, or at least warm enough to deform the crust, and then froze and expanded, cracking the surface as it did so. But Charon's poles are different, dramatically different. Both the North Pole and the South Pole are coated in dark reddish-brown material. The colour is rich, deep rust red in enhanced colour images, and completely inconsistent with the grey-white of the rest of Charon's surface. Something deposited this material, something chemical and complex, not geological in the usual sense. For decades after Pluto's moon was discovered in 1978, planetary scientists suspected that the dark poles were related to Pluto's atmospheric escape. The basic idea was direct. Methane escaping from Pluto's upper atmosphere gets trapped at Charon's cold poles, freezes there, and is then processed by ultraviolet radiation from the sun into heavier, more complex organic compounds, a class of substances called tholins, complex reddish-brown organic molecules that form when simpler hydrocarbons and nitrogen compounds are exposed to UV radiation. Tholins are found throughout the outer solar system, on Pluto's dark regions, on Titan's surface, on various other Kuiper belt objects. Their distinctive reddish-brown colour is a kind of chemical signature. The hypothesis made sense, but it was difficult to test directly, because testing it required being able to measure Charon's thermal properties separately from Pluto's, and until Webb, no instrument was sensitive enough to do this cleanly. Webb's MIRI observations in October 2022 and the spectroscopic session in May 2023 changed this. For the first time, the team measured Charon's thermal light curve independently of Pluto's. The results were unambiguous. Charon's polar regions show thermal and spectral properties that are clearly distinct from its water ice, dominated mid-latitudes. The polar material has different thermal inertia. It absorbs and releases heat differently than water ice, consistent with an organic material deposited from an external source rather than geological ice native to Charon's interior. The JWEST data also provided more detailed information about what Charon's polar material is. The spectroscopic observations revealed signatures of ammonia-based compounds mixed in with the water ice alongside the darker organic material. The chemical picture that emerged was of a surface that has been receiving material from Pluto for a very long time, methane arriving, freezing, being transformed by radiation into tholins and related organic compounds, accumulating over billions of years into a layer thick enough to significantly change the thermal and optical properties of the polar regions. The researchers reported in their 2025 papers that this interaction, material from one world's atmosphere drifting through space and being deposited on a neighbouring world's surface, appears to be unique in the solar system. Not rare. Unique. No other planet-moon system we have studied shows this kind of atmospheric transfer. Every other moon either has its own atmosphere and its own photochemistry, or has no atmosphere and receives in effect nothing from its parent planet. Only in the Pluto-Charon system is the geometry right, the atmospheric escape rate right, and the cold trapping mechanism at the destination right for this kind of sustained exchange to operate. Think about what that means for Charon's surface. Charon's dark poles are not just interesting geological features. They are a record, a physical, chemical, accumulated record of what Pluto's atmosphere has been doing for billions of years. Every methane molecule that escaped from Pluto's upper atmosphere and landed on Charon contributed to that record. The depth of the dark material at the poles encodes information about the history of Pluto's atmospheric activity. The chemistry of the polar deposits carries information about the composition and temperature of the atmosphere that produced them. Charon is Pluto's diary, written in organic chemistry on the coldest surfaces of the outer solar system. JWEST did not just detect this process, it measured it in enough detail to constrain the thermal inertia of the deposited material, to confirm that the polar chemistry is different from the mid-latitude chemistry, and to establish that the differences are consistent with the atmospheric transfer model rather than any alternative geological explanation. The confirmation was clean. There is one more dimension to this finding that deserves to stand on its own for a moment. The organic chemistry happening on Charon's poles, the transformation of methane into complex organic molecules under ultraviolet radiation, is not exotic. It is, in fact, a version of chemistry that we understand quite well from laboratory experiments and from the study of other haze-bearing worlds. Tholins form readily when you expose nitrogen-hydrocarbon mixtures to UV radiation. They are among the most common complex organic molecules in the outer solar system, and they are made of carbon, nitrogen, and hydrogen atoms, the basic building blocks. This does not mean life. Let's be careful here. The existence of organic molecules on Charon's poles is not evidence of biology. Tholins form abundantly through purely physical chemistry, with no biological input required. The point is not that Charon is alive or that Pluto is seeding life on its moon. The point is that the chemistry is real, it is complex, and it is happening in a place and in a way that has no parallel anywhere else in our solar system. Pluto is feeding its moon. Not metaphorically, physically through atmospheric escape, cold trapping and radiation-driven chemistry, Pluto has been painting Charon's poles with its own organic chemistry for billions of years, and JWEST confirmed it. That finding alone would justify the existence of this script. But there are more. Pluto is strange. But it is not entirely alone in being strange in this particular way. When the researchers published their 2025 findings, they noted explicitly that Pluto's haze-dominated atmosphere has parallels elsewhere in the solar system. The worlds they pointed to are Titan and Triton, Saturn's largest moon and Neptune's largest moon, respectively. Both are icy worlds in the outer solar system. Both have nitrogen-methane atmospheres. Both show evidence of complex photochemical haze. And both are now being considered in a new light, informed by what JWS found at Pluto. Titan is the most familiar of these three. It is in fact the only moon in the solar system with a thick atmosphere, thick enough to create surface pressure slightly higher than Earth's sea level pressure. Despite Titan being smaller than Earth and much colder, Titan's atmosphere is mostly nitrogen with a few % methane, and the chemistry between these two compounds under ultraviolet radiation from the sun produces a rich suite of organic molecules and an orange-brown haze that shrouds the surface. From space, Titan looks like a fuzzy orange ball, the haze so thick that visible light cameras cannot see through it to the surface below. The European Space Agency's Huygens probe, which descended through Titan's atmosphere in 2005, passed through layer after layer of this haze on its way down. The composition of Titan's haze has been studied in detail. The tholins and related organic molecules that form in it are chemically complex. Some of them are among the most sophisticated organic molecules found anywhere outside of living things on Earth. The chemistry of Titan's atmosphere is often discussed in the context of prebiotic chemistry, the kind of organic chemistry that preceded life. Triton, Neptune's largest moon, is less well studied. The only close-up observation we have of it comes from Voyager 2's flyby in 1989, but it shows signs of a thin nitrogen atmosphere with seasonal activity, active geysers, and surface features consistent with volatile ice cycling similar to Pluto's. Based on current models, Triton may have a haze layer with properties similar to Pluto's. What the DREST findings suggest is that Pluto, Titan, and possibly Triton represent a class of worlds, nitrogen-methane worlds with haze-dominated atmospheric chemistry, and that the haze on these worlds is not just an atmospheric peculiarity, but a central feature of how these worlds work. The temperature structure, the energy balance, the surface chemistry, the volatile cycling, all of these are shaped by the haze in ways that are only now beginning to be quantified. There is something useful in thinking about why three such different worlds would share this chemistry. Titan is enormous for a moon, larger than the planet Mercury, and with an atmosphere so thick it creates surface pressure higher than Earth's. It orbits Saturn, well inside the gravitational influence of one of the solar system's largest planets. It has methane lakes on its surface. It is geologically active in ways related to its thick atmosphere and tidal heating from Saturn. It is, by any measure, a complex and well-resourced world. Triton, Neptune's largest moon, is almost certainly a captured Kuiper Belt object, a world that formed in the outer solar system and was grabbed by Neptune's gravity at some point in the distant past. Its orbit is retrograde, meaning it circles Neptune in the opposite direction of Neptune's rotation, a clear sign it was not born in Neptune's system but arrived from elsewhere. Triton has a thin nitrogen atmosphere, active geysers of nitrogen, and a surface that is geologically young. It is in many ways more similar to Pluto than to any of Neptune's other moons. Pluto is neither of these things. It is not large and resource-rich like Titan. It is not a captured moon being tidally heated by a giant planet like Triton. It is a freer-standing Kuiper Belt world orbiting the Sun at its own leisurely pace, receiving only the faint warmth of a distant star and the internal heat of its own radioactive decay. And yet it has the same fundamental atmospheric chemistry as both Titan and the probable Triton, nitrogen, methane haze of complex organics. The commonality is the starting materials. Nitrogen and methane, exposed to ultraviolet radiation, produce complex organic chemistry. It doesn't matter much what the energy source is, or how large the world is, or how warm or cold. If you have nitrogen and methane and UV radiation, you will get haze. What differs between the worlds is the rate, the scale, the temperature at which it happens, and what the haze then does once it has formed. On Titan, the haze is thick enough to obscure the surface entirely. On Pluto, it is thin enough that the surface is visible. On Triton, if it exists, it is thinner still. But in all three cases, the chemistry is the same in kind. There is a human dimension to this that Shi Zhang, the researcher who proposed the haze thermostat hypothesis, pointed out explicitly in the wake of the 2025 confirmation. Understanding how haze behaves in extreme environments, he said, is not just about Pluto. Before Earth accumulated significant oxygen in its atmosphere, a transformation that took place roughly 2.4 billion years ago during what scientists call the Great Oxidation Event, Earth's own atmosphere was mostly nitrogen with hydrocarbon chemistry. Methane was present in significant quantities. Haze may have formed. The organic chemistry of the early oxygen-free Earth may have resembled, in broad strokes, the chemistry that operates on Pluto's surface today. This parallel does not claim that life exists on Pluto. It does not claim that Pluto is a good environment for life. Pluto is extraordinarily cold, extraordinarily remote, and receives only a fraction of the solar energy that Earth does. The organic chemistry happening there is driven by physics, not biology. But the chemistry itself, the reactions between nitrogen and methane under ultraviolet radiation, the formation of complex organic molecules from simple starting materials, is a version of chemistry that may have been relevant to life's origins on Earth. What Pluto offers is a laboratory, a place where a version of early Earth atmospheric chemistry is operating right now, frozen in time in the cold of the outer solar system, accessible to observation with the right instruments. Not a place to look for life, a place to look at chemistry. A window, of a kind, onto conditions that may have existed on our own planet billions of years ago. That window opened in 2025 when the DREST results were published. It was opened by a prediction that had waited 8 years to be tested. Science at the edges of the solar system requires a particular kind of patience. You cannot go there quickly. The distances are too large. The fastest spacecraft we have ever launched, New Horizons, which travelled faster than any previous probe at its launch, took 9.5 years to reach Pluto, and it arrived going so fast it couldn't slow down. You cannot land instruments. You cannot drill into the surface. You cannot collect samples and bring them back. You observe from a distance, you build models, you make predictions, and then you wait for an instrument capable of testing those predictions to be built, launched, and aimed at the right target. This is the story of how the haze thermostat hypothesis went from a paper published in 2017 to a confirmed result published in 2025. New Horizons flew past Pluto in July 2015. In the days and weeks that followed, the science team worked through the data as it arrived at Earth, a process that took more than a year, because New Horizons' radio transmitter was slow and the data was voluminous. Among the most striking early results were the atmospheric observations. Pluto's upper atmosphere was colder than expected, and it was full of haze. The haze appeared in the backlit images as multiple distinct blue layers extending hundreds of kilometers above the surface. The blue color was the first hint that something interesting was happening. Haze that scatters sunlight into blue wavelengths is composed of particles of a specific size range, suggesting organic material of some complexity. ground-based spectroscopy had already identified methane and nitrogen in Pluto's atmosphere. New Horizons confirmed the haze was ubiquitous and complex. For Shi Zhang, then a researcher at NASA Ames Research Center and later a professor at Santa Cruz, the cold upper atmosphere and the pervasive haze prompted a specific question. How was the atmosphere staying so cold? The gas cooling models being used to explain Pluto's atmospheric temperature weren't matching the data well. Something was removing heat more efficiently than gas molecules alone could account for. Zhang worked through the physics. Haze particles, unlike gas molecules, have a large surface area relative to their mass. They can absorb solar energy during the day and radiate it away as infrared emission very efficiently. If the haze particles in Pluto's upper atmosphere were absorbing sunlight and radiating the energy back to space as mid-infrared light, they would effectively act as a cooling agent, an additional energy loss mechanism that the gas-only models were missing. He published this hypothesis in 2017 with a co-author in the journal Nature Geoscience. The paper laid out the physics, built a model that showed the haze cooling mechanism could explain Pluto's cold upper atmosphere, and, this was the crucial step, made a specific quantitative prediction. If the haze is cooling Pluto's atmosphere by radiating energy as mid-infrared emission, then Pluto should be detectable as an unusually bright source in mid-infrared wavelengths, brighter than a surface-only model would predict. The prediction required sensitivity in the 10 to 30 micrometer wavelength range that no operating telescope could achieve for an object at Pluto's distance. The paper was received with skepticism in parts of the planetary science community. Haze-controlled atmospheric energy balance was truly unusual. The standard models, based on gas molecule behavior, had worked well enough for other worlds. The idea that particles, tiny suspended organic compounds, could dominate the entire thermal budget of a planetary atmosphere required either accepting that Pluto was uniquely strange or that there was something fundamentally wrong with the existing models. Zhang was, by his own later account, told it was a crazy idea. He kept the paper published. The prediction kept standing. And 4 years later, on Christmas Day 2021, NASA launched the James Webb Space Telescope. DWEST was not built for Pluto. It was built to study the early universe, the first galaxies, the atmospheres of exoplanets, the chemistry of star-forming regions and protoplanetary disks. Pluto is an asterisk in its observing program, a small target in the outer solar system, interesting to planetary scientists but not central to the telescope's primary scientific mandate. But DWEST's capabilities, the mid-infrared sensitivity of MIRI, the ability to separate closely spaced sources, the stability of its orbit at the L2 point, made it uniquely capable of testing the prediction Zhang had published 4 years before its launch. The proposal to observe Pluto with MIRI was approved. The observations were scheduled for October 2022, the first apparition during which Pluto would be observable. And on those 6 nights in October 2022, DWEST aimed MIRI at the point in the sky where Pluto was, a point that, to MIRI, was a faint source of heat against the cold background of deep space, and measured. The data came back. The team spent months analysing it, building thermal models, testing the surface-only hypothesis, testing the haze plus surface hypothesis, comparing the fits to the observations. The May 2023 spectroscopic session added more data. The analysis continued through 2023 and into 2024. In June 2025, in Nature Astronomy, the paper appeared. Tanguy Bertrand as lead author, Shi Zhang as co-author. The title did not bury the result. The paper confirmed, with the first clean mid-infrared observations of Pluto ever made, that the haze controls Pluto's atmospheric heat balance. The prediction was correct. 8 years between the prediction and the confirmation. 8 years in which the hypothesis sat in the literature, periodically cited and periodically contested, waiting for a telescope sensitive enough to test it. When that telescope finally looked, the crazy idea turned out to be right. Zhang's reaction, reported in the press coverage of the 2025 results, was not triumphant. It was quiet. He talked about what the result meant for understanding haze in extreme environments. He talked about the implications for Titan and Triton. He talked about the connection to early Earth's atmospheric chemistry. He said, Pluto sits in a really unique spot in the range of how planetary atmospheres behave. That is the kind of statement that only makes sense after you have spent 8 years being told your idea is crazy and then finding out it was right. Quiet, accurate, not a victory announcement. A fact. The October 2022 observations with MIRI's photometric mode told the team what they needed to know about the thermal light curves. The haze was there. It was emitting. The hypothesis was confirmed, but the May 2023 observation was different in kind. In May 2023, MIRI operated in its spectroscopic mode. Instead of measuring the total brightness of Pluto at a few fixed wavelengths, it captured a continuous spectrum, a record of Pluto's infrared brightness across the full wavelength range from 4.9 to 27 micrometers. This spectrum is, in the most literal sense, a fingerprint. Every substance that is present in Pluto's atmosphere or surface, if it absorbs or emits infrared light at some wavelength in this range, will leave its mark. The spectral range from 4.9 to 27 micrometers had never been observed for Pluto before. Previous instruments simply did not have the sensitivity to measure Pluto cleanly at these wavelengths from Earth's distance. The data that came back from the May 2023 session opened a part of the electromagnetic spectrum that had been, until that moment, entirely unexplored for Pluto, a truly new window onto a world that had been studied for nearly a century. What the spectrum showed was chemically richer than the models had captured. The surface signatures were clear and expected, at least in broad outline. Methane ice showed up clearly. Methane absorbs infrared light at specific wavelengths between 7 and 9 micrometers, and the signature was strong. Nitrogen ice, the dominant surface volatile, showed up in the spectral shape of the thermal emission. Carbon dioxide features were visible. So far, this was largely consistent with what ground-based observations and New Horizons had established. But there were surprises. Deuterated methane, methane in which one of the 4 hydrogen atoms has been replaced by deuterium, the heavier isotope of hydrogen, showed a detectable signature. The ratio of normal methane to deuterated methane carries information about the conditions under which the methane originally formed and how it has been processed since. Ethylene ice, a more complex hydrocarbon with 2 carbon atoms, showed up at wavelengths around 10 micrometers. This was a detection that had not been previously confirmed for Pluto's surface, and its presence adds to the picture of active organic chemistry in Pluto's surface ices. The haze emission itself was present in the spectrum as a broad contribution across the mid-infrared wavelengths, consistent with organic particles of the kind predicted. Similar in their spectral properties to the haze particles studied in Titan's atmosphere and in laboratory experiments with nitrogen hydrocarbon photochemistry. What the full spectrum revealed was not a simple world with a few well-understood ices and a thin gas layer above them. It revealed a chemically active surface where multiple volatile ices are present simultaneously, where the chemistry between them and the UV radiation from the sun is ongoing, and where the products of that chemistry, more complex organic molecules, are accumulating both in the surface ices and in the atmospheric haze above. The phrase unexpected chemical richness appears in the scientific literature around these results. It is the kind of phrase that planetary scientists use carefully because it reflects a genuine gap between what the models predicted and what the data showed. The models were good. They were built from years of careful observation with every instrument that had ever been pointed at Pluto. They were not wrong about the basic inventory of Pluto's surface chemistry. But they were incomplete. The full mid-infrared spectrum showed more than the models had captured. This is what happens when you open a new observational window, not a dramatic overthrow of existing understanding. Something more subtle and more honest. The existing understanding turns out to have been incomplete in ways that only become visible when you can finally see clearly enough. Pluto's surface and atmosphere are doing chemistry. The chemistry is ongoing. The products of that chemistry are complex organic molecules that form under ultraviolet radiation, accumulate on the surface and in the haze, and, as the earlier chapter established, are slowly transferred to Charon over time. The chemical system is active, it is connected, and it is rich enough that the best models built before Dwest couldn't fully capture it. All of this, the haze thermostat, the geological youth, the nitrogen heartbeat, the atmospheric transfer to Charon, the spectral richness, is happening right now. As you are watching this, at a distance of 5.5 billion kilometers from Earth, on a world that most people think of as the rock we stopped calling a planet. Slow down for a moment, set aside the data and the thermal light curves and the spectral signatures. Think about what Pluto is actually like as a place. The Sun, from Pluto's surface, looks like a very bright star. It is the brightest object in the sky, by far, far brighter than any other star, bright enough to hurt your eyes if you looked at it directly, even from that distance. But it is a point of light, not a disk. The warmth it provides is real. Pluto's surface temperature of minus 229 degrees Celsius is actually warmer than it would be if Pluto had no atmosphere and no haze, because even the thin atmosphere creates a slight greenhouse effect and the haze traps some additional heat. But it is cold in a way that puts every cold thing you have ever experienced into a different category. The nitrogen glacier under your feet is a solid that behaves like a slow, viscous liquid over geological time, but at the time scale of a human life, it is rigid. The water ice mountains to the north are as hard and immovable as granite. The sky is not black. Not quite. During the day, the thin nitrogen atmosphere scatters the sunlight in a way that would give the sky a faint blue tint, confirmed by New Horizons' backlit images of the haze layers. You would be standing inside the haze. It begins at the surface and extends hundreds of kilometers upward, each layer slightly different in density and composition, each one a record of the ongoing organic chemistry being driven by that distant but present sun. The haze particles are small, nanometer to micrometer scale, and they drift slowly through the air, absorbing and releasing energy as the day progresses. In the daytime, they absorb solar energy and heat up slightly. As the temperature changes, they rise and fall in response to the atmospheric circulation driven by the nitrogen glacier's sublimation cycle. They are alive in the sense that physical systems are alive, not biological, but dynamic, changing, responsive to the conditions around them. The glacier itself is not white in the way that a snowfield on Earth is white. It is pale, almost luminous, and divided into those polygon cells, each one tens of kilometers across, each one slowly churning as the convective cells below push warmer material up and cooler material down. The boundaries between cells are marked by shallow troughs a few meters deep, where the descending material accumulates. If you walked across the glacier, you would cross ridge after shallow ridge, the terrain gently undulating under your feet, the pale ice stretching to the horizon in every direction. At the edges of the glacier, the terrain changes abruptly. The water ice mountains rise steeply from the glacier's shore. Their surfaces covered with methane snow at the higher elevations, bare water ice below, streaked with dark lines where wind-blown material from the glacier has been deposited. These mountains are old. They formed early in Pluto's history and have survived largely intact because water ice at these temperatures does not deform or erode on human timescales. Charon hangs in the sky. It is large, much larger in apparent size than our moon from Earth, because it is big relative to Pluto and orbits close. Pluto and Charon are tidally locked to each other, meaning each keeps the same face toward the other at all times. From the hemisphere of Pluto that faces Charon, the moon sits more or less fixed in the sky, enormous and pale. Its dark reddish poles visible even from this distance. Those dark poles are, as we now know, made of chemistry that travelled from the atmosphere above your head, escaped upward, drifted across 19,500 kilometres of empty space, and settled there. In the sky above Charon, the haze rises. On the far side of Pluto, the hemisphere that never sees Charon, the landscape is different. Darker, more heavily cratered older terrain that has not been renewed by the glacier's reach. The surface there is the ancient Pluto, the Pluto that formed 4.6 billion years ago and has been slowly accumulating craters ever since. It is cold and dark and still. Dwest cannot see the individual mountains or the glacier's polygon cells or the dark streaks on the highland terrain. Its resolution at this distance is too low for that. What it can see, what it measured, is the heat that all of these features are producing and emitting. The light curves that showed a warm region corresponding to the nitrogen glacier's sublimation, and a cooler region on the darker hemisphere, and the steady mid-infrared glow of the haze overhead. The data is a sketch of the place, not a photograph. But a sketch is enough, sometimes, to know that something real is there. Something real is there, and it is stranger and more active and more connected to the rest of its system than anyone expected. There is a moment in the history of Earth that is difficult to conceptualize, but important to try. 4 billion years ago, give or take, Earth's atmosphere looked nothing like it does today. There was no significant oxygen. The nitrogen was there, as it is now, making up the bulk of the air. But instead of the oxygen that makes Earth breathable, instead of the ozone that shields the surface from ultraviolet radiation, there was methane. And hydrogen. And carbon dioxide. And the chemistry between these compounds under the UV radiation that poured down from the young sun, more intense in some wavelength than today's sun, was producing complex organic molecules in the atmosphere. The sky was not blue. It may have been orange or brown, hazed with photochemical products, in the way that Titan's sky is orange today. This atmosphere, nitrogen, methane, hydrocarbons, no oxygen, heavy with complex organic chemistry, is what existed on Earth before life began to change it. It is, in some broad chemical sense, the atmosphere within which life either arose or into which early life was born, depending on when you draw the line between chemistry and biology. It is the atmospheric context for the origin of life on Earth. And it is, in broad strokes, chemically similar to Pluto's atmosphere today. Xi Shang made this connection explicit in the context of the 2025 JWS results. Understanding Pluto's haze-dominated atmospheric chemistry, he argued, is not only about Pluto. It expands our understanding of how haze behaves in nitrogen-methane atmospheres across a range of conditions, and those conditions include the early Earth. Before oxygen accumulated and changed everything, Earth's atmospheric chemistry may have produced haze particles, complex organics, and nitrogen hydrocarbon photochemistry of the kind that JWST is now studying on Pluto in real time. This connection requires careful handling. It does not mean that Pluto is a good model for life. Pluto is cold beyond any cold relevant to Earth biology, remote beyond any accessible distance, and receives only a tiny fraction of the solar energy that early Earth had. The chemistry on Pluto is happening slowly, driven by faint UV radiation at enormous distances, while the chemistry on early Earth would have been far more energetic and far more dynamic. But the starting materials are similar. The reactions are similar in type. The products, complex organic molecules of the tholin family and related compounds, are similar to the kinds of molecules that some researchers argue were important in prebiotic chemistry on early Earth. There is a chemical continuity here that goes beyond metaphor. What JWST has done, by confirming the haze thermostat model and measuring Pluto's atmospheric chemistry in detail, is provide the first direct observational data for this kind of extreme condition: nitrogen-methane, haze-dominated photochemistry. The laboratory experiments that researchers use to simulate these reactions have known for decades that complex organics form. Titan's atmosphere has shown that the chemistry operates in nature. Pluto now shows that it operates even under conditions far more extreme than Titan, at greater distance, in a thinner atmosphere, at lower temperatures. Let's think about what extreme means in this context, because it matters for understanding what Pluto's chemistry tells us. The nitrogen-methane photochemistry that produces Pluto's haze requires UV radiation from the Sun. At Pluto's distance, the UV intensity is roughly 1,600 times weaker than at Earth. This means the reactions proceed slowly. The haze forms slowly. The organic compounds accumulate slowly. The total inventory of complex organic material on Pluto's surface and in its atmosphere, which has been building for billions of years, reflects this slow but continuous chemistry operating over an enormous span of time. The slowness is compensated for by the duration. On early Earth, the UV environment was different, possibly more intense in certain wavelengths, because Earth's early atmosphere lacked the ozone layer that today shields its surface. The reactions were faster, the chemistry was more energetic. But the starting materials were similar: nitrogen, methane, and various hydrocarbon compounds exposed to a UV-bearing sky. The products of that chemistry, complex organic molecules including amino acid precursors, nuclear base precursors, and other compounds relevant to prebiotic chemistry, may have been among the building blocks from which life eventually emerged. Pluto is not producing amino acids. The temperatures are too low and the energy input too faint for the specific reactions relevant to life as we understand it. But it is producing the same class of organic molecules, the tholins and hydrocarbon polymers and nitrile compounds, that early Earth likely had in its atmosphere, and that laboratory experiments show can serve as starting materials for more complex prebiotic chemistry when given more energy and warmer conditions. If nitrogen-methane photochemistry with haze is a robust atmospheric process, one that operates across a wide range of conditions, then it may also operate on exoplanets. The universe is full of nitrogen-bearing worlds with organic chemistry. Some of them will have conditions that fall in this chemical regime. Understanding what that chemistry does, how it evolves over time, and what kinds of complex molecules it produces is relevant not just for the handful of worlds in our own solar system where we can directly observe it, but for the entire class of worlds across the galaxy that we cannot yet visit. Pluto is, in this sense, a reference point, a data point at one extreme of a parameter space that spans from early Earth to Titan to Triton to unknown worlds around other stars. Every measurement Joest makes of Pluto's atmospheric chemistry adds to our understanding of what nitrogen-methane photochemistry does at cold temperatures and low energy inputs. That understanding has implications that extend far beyond the Kuiper belt. We almost didn't look closely enough to find it. We filed this world away in a category and moved on. The category was not wrong. Pluto is a dwarf planet by the OWL's definition, and that classification is scientifically defensible. But the dismissal that accompanied the reclassification, the sense that Pluto was no longer worth sustained attention, meant that serious proposals for an orbital mission to Pluto have been slow in coming, despite the striking complexity revealed by New Horizons and now deepened by JUST. The chemistry was always there. It will keep operating long after every human who has ever looked at the night sky is gone. The question is only whether we look carefully enough, and with the right instruments, to understand what it is telling us. Everything described in this script so far comes from confirmed observations. The haze thermostat is confirmed. The geological youth of Sputnik Planitia is confirmed. The nitrogen heartbeat is confirmed. The Pluto to Charon atmospheric transfer is confirmed. These are findings grounded in peer-reviewed data from actual measurements. What comes next is different. It is a hypothesis, a strong and coherent hypothesis, consistent with multiple lines of evidence, taken seriously by serious researchers, but it has not been confirmed. It cannot be confirmed with current instruments. Confirming it would require an orbiter in the Pluto system, and as of 2025, no such mission has been approved. This chapter presents the evidence and the reasoning without pretending the conclusion is settled. The hypothesis is this: Pluto may have a liquid water ocean beneath its surface. Let's work through why anyone would suggest this for a world this cold. The first clue is the location of Sputnik Planitia itself. The glacier sits in a basin on one specific hemisphere of Pluto, the hemisphere that faces directly away from Charon. This positioning is not random. Pluto and Charon are tidally locked to each other, and tidal locking creates a situation where the orientation of a planet with respect to its moon is determined by the distribution of mass within the planet. A heavy mass inside Pluto would tend to either face toward Charon or face directly away from it. There are two gravitationally stable orientations. Sputnik Planitia sits in one of these positions. The implication is that the region beneath the glacier is denser than the surrounding terrain. How could a basin of lighter ice be underlain by something denser? One answer is a subsurface ocean. Water is denser than ice. If a liquid water layer exists beneath Sputnik Planitia, the basin above it is actually sitting on top of denser material, and the orientation of the glacier relative to Charon makes sense. Without the subsurface ocean, you need a different explanation for why this particular low-lying basin ended up in exactly the tidally stable orientation facing away from Charon. The second clue is the geological activity at the surface. The convection cells in Sputnik Planitia require a heat source. The radioactive decay in Pluto's interior provides heat, but whether it provides enough heat, without additional help from a liquid water layer that stores and redistributes thermal energy, is a matter of ongoing modelling. Some researchers argue that the surface activity is fully explained by the radioactive heat alone. Others suggest a subsurface ocean makes the models work more cleanly. The third clue is Charon. New Horizons found evidence that Charon once had an internal ocean of its own, a body of liquid water that subsequently froze. The evidence is the long belt of tectonic fractures across Charon's equator, a feature consistent with the surface cracking as an internal ocean froze and expanded. Charon is smaller than Pluto and receives less radioactive heat. If Charon once had an internal ocean, but has since frozen it, Pluto, larger, warmer, with more internal heat, might still have one. The fourth clue is the presence of flowing ice features at the edges of Sputnik Planitia, ice lobes that appear to flow outward from the main glacier into the surrounding terrain, similar in form to glaciers on Earth. This ice flow requires material that is warm enough to deform, even at Pluto's temperatures, which is possible for nitrogen ice, but requires specific conditions. None of these clues is conclusive on its own. Together, they suggest that an internal ocean is a viable and perhaps preferred explanation for several features of Pluto's geology. But viable and preferred is not the same as confirmed. The only instrument that could confirm a subsurface ocean would be one operating in Pluto's orbit, either a magnetometer detecting the electromagnetic signature of a conducting liquid layer, or a seismometer measuring internal oscillations that would reveal whether the interior is solid or partly liquid. JWST cannot do this. JWST measures surface and atmospheric thermal emission from billions of kilometers away. It cannot see beneath the surface. What it can confirm, and what it has confirmed, is consistent with a world that is geologically active, thermally unusual, and chemically complex in ways that a completely solid, frozen-through world might not produce. If the ocean exists, Pluto joins a growing list of outer solar system worlds where liquid water persists far from the Sun. Europa, one of Jupiter's moons, almost certainly has a subsurface ocean. So does Ganymede. So does Callisto probably, Enceladus, one of Saturn's moons, actively vents material from its internal ocean through geysers at its south pole. Titan may have a subsurface ocean. The outer solar system, which once seemed to be a cold and largely dead place, turns out to be full of liquid water, just not on the surface. Underground, insulated by rock and ice from the cold of space, warmed by tidal forces or radioactive decay, liquid water persists in places where the surface temperature is far too cold for it to exist at the surface. Pluto may be one of these worlds. The evidence points in that direction. The confirmation awaits a mission that has not yet been planned. In August of 2006, the International Astronomical Union held its General Assembly in Prague. By a vote of 237 to 157, with 17 abstentions from a membership of thousands, the majority of whom were not in attendance and were not able to vote electronically, the AO passed Resolution B5. It defined a planet as a celestial body that orbits the Sun, has sufficient mass for its self-gravity to assume a roughly spherical shape, and has cleared the neighbourhood around its orbit. Pluto met the first two criteria. It did not meet the third. It was reclassified as a dwarf planet. The scientific reasoning was defensible. Pluto shares the outer solar system with a large population of Kuiper belt objects, icy bodies with similar compositions and orbital characteristics. It is not uniquely dominant in its region the way Jupiter dominates the inner solar system or Earth dominates the terrestrial zone. The definition was an attempt to make the category of planet mean something more specific than round and orbits the Sun. The scientific controversy over whether the definition itself is well constructed is ongoing and is not the subject of this chapter. Some planetary scientists continue to argue that the EAO's definition is poorly designed, that it is geocentric in the sense that it only applies within our solar system, and that it would exclude geologically active worlds far larger than Pluto if they were orbiting in a crowded region. That is a genuine scientific debate. What this chapter is about is the cultural effect of the demotion on how much attention Pluto received. After 2006, Pluto became, in the popular imagination, the object of mild nostalgic affection, the planet that got fired, the underdog. the little world that planetary scientists voted away. It was written about with a mix of humour and slight sentimentality. Elementary school children continued to learn about it, usually as a footnote or a cautionary tale about scientific definitions. It was not, for the most part, a world that commanded serious scientific urgency. New Horizons changed some of that. The 2015 flyby images were striking enough to re-energise public interest and to remind planetary scientists that Pluto was scientifically complex in unexpected ways. But New Horizons was a single pass. It was not an orbital mission. And in the years since 2015, despite the revelations of that flyby, no dedicated orbital mission to Pluto has been approved by NASA or any other space agency. Proposals have been written, concepts have been studied, but no mission has been selected and funded. Compare this to Europa. Jupiter's moon Europa is widely considered a high-priority target for astrobiology because of its probable subsurface ocean. NASA's Europa Clipper mission launched in October 2024 and is currently en route to Jupiter. The mission was approved, funded and launched. Europa is a moon, not even a planet, but it has received the full weight of institutional commitment and scientific resources that come with a flagship mission. Pluto, with its confirmed haze-dominated atmosphere unlike any other in the solar system, its geologically active surface, its ongoing atmospheric transfer to Charon, its possible subsurface ocean, and its relevance to the chemistry of the early Earth and potentially to nitrogen-methane worlds throughout the galaxy, Pluto has a concept study, not a mission. The question that JWST's 2025 findings make harder to avoid is whether the demotion, or more precisely, the dismissal that accompanied it, contributed to this disparity. If Pluto had remained a planet in the popular and scientific imagination, would an orbital mission have been proposed sooner? Would the urgency have been different? These questions cannot be answered definitively. Science prioritization is complex, driven by many factors beyond cultural status. But the question is not entirely unfair. The OWS definition was designed to clarify a scientific category. The unintended consequence was a cultural message: Pluto is not special enough to warrant full planetary attention. JWST's results suggest that the cultural message may have been wrong, even if the scientific classification was defensible. Pluto is not special in the way that Earth or Jupiter is special, not in size or gravitational dominance or orbital importance. But it is special in other ways. In the specificity of what it does, in the uniqueness of its atmospheric chemistry, its surface activity, its relationship with its moon. The scientific community is beginning to respond. The 2025 publications prompted renewed discussion of a Pluto orbiter concept. Whether that discussion leads to a funded mission remains to be seen. In the meantime, WOS will continue to observe Pluto from 5.5 billion kilometers away, measuring its heat and its chemistry with instruments that were not designed for it, but that turn out to be exactly what was needed. The world was always doing this. We just didn't look closely enough, or with the right instruments, or with sufficient urgency to find out. Let's go back to the beginning. A telescope aimed at a point of heat, more than 5 billion kilometers from Earth. The point of heat is Pluto. The telescope is JWST. The instruments are measuring wavelengths of infrared radiation that have never been measured for this world before, in a range of the electromagnetic spectrum that was, before 2022, simply closed, not because no one wanted to look, but because no instrument existed that could look clearly enough. What they found is a record. Not a record in the metaphorical sense, a record in the physical, chemical, planetary sense. Pluto carries a record of everything it has been doing for billions of years. The haze that rises in its atmosphere carries the signature of continuous photochemistry, sunlight meeting nitrogen and methane and producing increasingly complex organic molecules over geological time. The glacier at its heart carries the record of its geological history, the oldest craters erased by convection, the young surface beneath marked by polygon cells that tell you something is still moving underneath. The dark poles of Charon carry the chemical record of every methane molecule that escaped from Pluto's upper atmosphere and drifted across 500 kilometers of empty space to freeze on a neighbouring moon. JWST did not change these records, it read them. For the first time, with instruments sensitive enough to separate the two-world signals, to measure the heat across the full mid-infrared spectrum, to detect the haze emission that a researcher in 2017 predicted would be JWST read what Pluto had been writing for a very long time. The reading confirmed that the haze controls the atmosphere. That confirmation matters because it changes how we model Pluto's climate, how we understand the nitrogen cycle, the seasonal redistribution of volatile ices, the rate of atmospheric escape. With the haze properly included in the models, the predictions for Pluto's long-term evolution change. The timeline over which Pluto will continue to have a detectable atmosphere changes. The rate at which Charon's poles are accumulating material changes. The connections between Pluto's chemistry and early Earth chemistry become more tractable to quantify. But behind the science there is something simpler. There is a world at the edge of the solar system. It is small and cold and receives only a tiny fraction of the sun's warmth. By every standard of planetary importance, size, mass, orbital dominance, proximity, accessibility, it barely registers. And yet it has a haze that works as a planetary thermostat in a way no other world's atmosphere does. It has a glacier that drives its own weather through daily sublimation and condensation, a heartbeat measured in nitrogen vapor and nitrogen ice cycling back and forth with every Pluto day. It has been slowly and continuously giving its own atmosphere to its moon for billions of years, writing its chemical history on Charon's poles in organic compounds that will outlast every mission we have ever launched. This was always happening. Before the New Horizons flyby showed us the heart-shaped glacier, before the 2006 demotion raised and then answered the question of what counts as a planet, before Clyde Tombaugh found a faint moving dot in a field of stars in 1930 and gave it a name, before any human being existed to care about any of it. Pluto was already doing this. The haze was already rising and cooling the atmosphere. The nitrogen was already sublimating from the glacier and condensing on the cold highlands. The methane molecules were already escaping and drifting toward Charon and freezing on the poles and being transformed by sunlight into something more complex. It will keep doing this. The haze will keep rising, the glacier will keep churning, Charon's poles will keep accumulating, long after JWST eventually runs out of fuel and drifts into a stable but inactive orbit around the Sun. Long after every telescope we have ever built has gone dark. Long after any reasonable definition of recent has passed. The most terrifying thing about Pluto is not the haze or the subsurface ocean or the unique atmospheric chemistry. It is the patience, the absolute, uncaring, continuous patience of a world that has been doing this for 4 billion years and will keep doing it for 4 billion more, whether anyone looks or not. We looked. Finally, with instruments sensitive enough to see the heat rather than just the light, we looked. And it turned out the crazy idea was right. The world we stopped calling a planet is doing something no other world in this solar system does. The haze rises. The nitrogen breathes. The molecules drift across empty space and settle on a dark moon. And somewhere at the edge of everything, 5.5 billion kilometers from here, Pluto keeps rotating. Indifferent, ancient, alive in every way that a world can be alive without being alive at all. Good night.